Hello, geographers. Welcome back. Chapter 5, Part 2, Atmospheric Moisture and Precipitation. Now, if you recall where we were before, we had talked about the steps to precipitation, and that included starting off with having dirty, moist air. Remember, we had to have two things in the air in order to have it rise and give us clouds and possibly precipitation. That air must contain water, and it has to have dust particles, or what we call condensation nuclei, or hygroscopic nuclei. Then the air has to rise and cool. So as it rises, it starts to cool adiabatically until it rises enough to reach its lifting condensation level. We get to relative humidity of 100%. Its dew point temperature, condensation will begin. So all those happen at the same time. Droplets will begin to grow. If they don't grow, we'll have a cloud, but we won't have rain. But if we do have those droplets growing, they'll coalesce together. That means come together. They'll get big enough, overcome the upward air movement and the friction, and ultimately we'll get some precipitation. So in order to get precipitation, we have to go through all of these various steps. If we look at the base of this cloud over here, again, we can now recognize that because a cloud is forming, we can visually see that air must have risen to its condensation level or lifting condensation level, LCL. It's reached its dew point temperature. Relative humidity at the base here will be 100%, and condensation is beginning. Droplets are probably growing within this cloud, and ultimately we could get some precipitation if those droplets grow enough. So this is just telling you a little bit about or showing you the droplet process. I'm going to lock myself out of here. There we go. So small droplets become larger, 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 and then they will fall out as precipitation if they get big enough. So our types of precipitation, they come in 5 typical varieties. There are more than this. These are, I'd say, the most popular 5 or the most common 5 forms of precipitation. And we will one by one go through rain, drizzle, snow, sleet, and hail. Always come back to this sheet, a little bit of a cheat sheet telling you some of the general details. So first of all, rain. Now rain is in the atmosphere because precipitation is defined as moisture falling through the atmosphere. Again, it must be falling through. So this is rain, the stuff, little streaks you see here. But on the ground, this is not rain. This is not rain anymore. This is now, because it's running off the surface, this is runoff. Remember our discussion of the hydrologic cycle. So rain is defined as liquid precipitation with a diameter of greater than 0.5 millimeters. So again, greater than 0.5 millimeters. Typically, it will have an oval shape as it's falling through the sky, but to be honest, it actually deforms a little bit as it falls through the atmosphere, so they can take on many shapes. The front or the bottom falling edge of that raindrop will get deformed a little bit, but most of them have somewhat of an oval shape. It's our number one form of precipitation. So as far as precipitation goes, the number one form is rainfall. Drizzle, on the other hand, is very much like rain. It's liquid precipitation, but here we see a diameter of less than or equal to 0.5 millimeters, and more of a spherical form because these droplets, they're pretty small, they're going to fall pretty slowly and not take on an aerodynamic or even a deformed shape. So our third form of precipitation is snow, and snow is solid precipitation. It has a very distinct shape. All snowflakes are based on this six-sided pattern, but that base form, that six-sided form, can change based on the temperature of the snow. We can see here that when the snow starts to form, if the snow is warm, like 32 degrees to 25 degrees Fahrenheit, we're going to get thin plates, six-sided. Gets a little bit colder, or if the air is a little bit colder at time of formation, it tends to form needles. Even colder, hollow columns with a six-sided shape. Then sector plates, 6 sides. And then finally dendrites. Dendrite means tree-like. So these are like little Christmas trees coming off of a central point. There's 6 of those on every snowflake when the temperature forms at 10 degrees Fahrenheit or colder. So again, a typical snowflake could look like this, or it could look like this, dependent on the temperature. But all snowflakes would have a six-sided shape, but every single snowflake will be a little bit different than every other snowflake. So this is what snow looks like on the ground. Unfortunately, we still call that snow for the most part, but technically the snow is while it's still in the air falling down. Again, at high latitude and high altitude or elevation. Falling snow, again, this looks very nice if you don't live in snow. So if you go to vacation and it's snowing, we get very excited, or if you have a rare snow day, we get very excited. But if you live in snow for more than a few weeks out of the year, you tend to not like snow so much anymore. Then we have sleet. Sleet is a mix of liquid and solid precipitation. So it's sort of like slush. In this case, it could be snow falling down through the atmosphere, hitting a warmer layer before it reaches the surface, and then that partially melts. Or it could be rainfall falling through the atmosphere and hitting a colder layer close to the atmosphere where it partially freezes. By the time it hits the surface, it's kind of a slushy mess. So sleet can look like this. Not so much fun. Look like this. So kind of like slush, half melted, half frozen. And finally, hail. Hail are concentric spheres of ice built from the inside outwards, kind of like an onion. And this would typically have a size of about a quarter of an inch to maybe 2 inches in diameter. The world record would be about 8 inches, close to volleyball size in diameter, coming out of the atmosphere. Not just one, but thousands, hundreds of thousands, possibly even millions of chunks of ice falling out of the atmosphere. Okay, if it's a quarter of an inch across, but if it gets bigger, watch out. That'd be very damaging. All hailstones form when we have warm air, warm, moist air, being lifted up in a cumulonimbus cloud. You're going to learn more about those later in this discussion. Cumulonimbus clouds have strong updrafts and downdrafts, updrafts and downdrafts within the cloud, and that allows moist, warm air to rise adiabatically, get to freezing level, and that ball of water starts to freeze as it grows. As it continues up, it will grow, and then it will come down. It will be forced down by gravity, and it will start to lose some of the molecules by bumping into those ice crystals moving upwards. So that upward, downward movement has them bump into each other, and it knocks pieces of ice off of each other. Also knocks ions off of each other, so it will give a little positive charge in some portions of the cloud, negative in other portions of the cloud. So this is also associated with lightning. So back to the ice balls going up and down. Every time it goes up, it grows, comes back down, shrinks a little bit, grows, gets smaller, grows, gets smaller. So as long as we have a strong updraft, the hailstones can get larger and larger and larger. We'll see them being built up. One cycle, another upward cycle, another upward cycle, etc. They could actually aggregate not just from the center, but sometimes by running into super cooled water on the way up and down, allowing it to grow also. So basically, we could end up with some very large hailstones, such as these. Imagine being hit by that at over 100 miles an hour. You probably would not survive that. And in fact, every year, people are killed by hail. So if you ever are experiencing a hailstorm, get under cover, but not under a tree, because again, that lightning and thunder is associated with the same kinds of storms. No, golf balls do not come out of the sky, but certainly golf ball size hail will come out of the sky. And this is the kind of damage it can do to your car if you're in an area where hail is prevalent. So some questions here before we move on. Okay, to which temperature must air cool for condensation to begin? So this is for rising air. What temperature must that air cool to? By the way, the same thing would occur for air just standing still and cooling all night. It would still have to cool to a certain temperature for condensation to begin. And I'm not looking for a specific temperature as per a thermometer. I'm looking for the name of that temperature to which air must cool for condensation to begin. I want you to think about that because that might be one of your quiz questions. Okay, what about for rising air? How high up must the air rise? So to what elevation must air rise in order for condensation to start forming a cloud? So specifically on this one, we're looking for the elevation. On the first one, we're looking for the temperature for condensation to begin. Can you tell me what is the main difference between rain and drizzle? Rain and drizzle. Which areas of the earth receive the most snowfall? Can you describe where most snowfall would occur on the planet? And what are the main steps to precipitation? So in order to get precipitation, what steps must be followed? So this next session deals with the classification of clouds. And there are a few words that we can learn that will help you to understand a little bit better the names we give to certain clouds. So if you understand a few prefixes, it's going to help. For instance, if you ever see the word cirro or cirrus, cirro means that the clouds are thin, they're wispy, high altitude clouds. They look like feathery clouds. They're blown by the upper level winds. They're made out of ice. So they're very faint, very thin. They look like horses' tails. And we describe that as being wispy in its appearance. Cumuloform, cumulo means heaped or kind of cotton ball-like. So a cotton ball-like cloud, especially with a flat base and puffy white sides, those are cumuloform clouds. Now, if you look at a cumuloform cloud, the gray in the bottom, the white on the sides, that's because sunlight is hitting the clouds, reflecting light on the tops and on the sides. The gray is basically the shadow of that reflected sunlight. Lastly, we see stratoform clouds. So strato means layered horizontally. They sort of form a blanket across the sky, these stratoform clouds. They usually are stable. It's air that it doesn't really want to rise too much, but it's sometimes forced to rise. Whereas cumuloform clouds, the ones we looked at over here, is white puffy ones, the ones that are heaped, when you see the white puffy sides, that means the air is typically warmer than the air around it, so they can want to continue to rise. We call that unstable. Now, one word you don't see here is alto, A-L-T-O, and that usually refers to middle layer or middle altitude clouds. They're not quite as high as the cirroform clouds, and they're not as low as the stratoform clouds, typically. As we can see here in this diagram, we have cirrus clouds, cirrocumulus clouds. So there's a little bit of puffy whiteness to them. They're a little bit unstable, but they're very high altitude made out of ice crystals. Then we have cirrostratus, layered horizontally, usually made out of ice crystals. They're so high in elevation. Altocumulus, so mid-level clouds with a puffy white appearance. Altostratus, mid-level clouds that are layered horizontally. Stratocumulus, those are basically a mix of blanket in the sky with a bit of instability, so they're a little bit puffy and white too. Stratus clouds, layered horizontally, they kind of make a blanket over the sky. They don't really produce any rain, whereas nimbostratus, we've just got introduced to the word nimbo, or the prefix nimbo, that means rain. So basically, we have a rainy stratus cloud with nimbostratus. Then we see cumulus clouds, that flat white bottom, puffy white sides, very typical cloud. If you were to draw a cloud or someone asked you to draw a cloud, you're probably going to draw a cumulus cloud, flat bottom, white puffy sides, etc. Now that one is typically a fair weather cloud, but can grow into a cumulonimbus. So basically, if allowed to continue to grow horizontally, and we get this anvil top, looks like a blacksmith's anvil right here. The upper level winds blow that top up away, shear it off. This is basically a cumulonimbus cloud, and this is a kind that has the updrafts and downdrafts that will produce strong, heavy rain, strong updrafts, so we get the hail formation and lightning and thunder associated with those clouds. The ones I really want you to know are cirrus, those high altitude feathery clouds made out of ice, stratus, the ones that basically are typically lower elevation, and they blanket the sky without rain. Nimbostratus, the ones that blanket the sky and give us rain. So is stratus, could easily turn into a nimbostratus cloud if forced upwards. And cumulus, the puffy white sides, heaped appearance, and cumulonimbus, the ones that start to give us the rain and probably the hail and thunder. So just 5 that I really want you to know. If this is a weather class, I want you to know a few more. So here are cirrus clouds. Cirrus clouds are those ones that look like a horse's tail. They're very feathery, wispy. They are found at high elevation. They're made out of ice, blown by the upper level winds, so they're spread out, dispersed quite a bit. Stratus clouds. We can see in this photo here that pretty much the whole sky is blanketed in gray. This is very good, like coffee or tea, hot tea weather. Very typical of Seattle or Portland or London. And I think for those reasons, you can kind of get a feel from this picture of the type of morning that you might get, or the type of day you might get with this gray, overhanging, cloudy weather, but really no rain. You might get some drizzle, but probably not any rain. This is in the La Crescenta area of Southern California, just north of LA. And here we see stratus clouds blanketing the Crescenta Valley. And in this case, no rain developed at this point, but we have that blanket of sky, that gray sky. Kind of weather you want to sleep into. Now, if a stratus cloud is forced to rise, which it is in this case here, we get nimbostratus clouds. We're starting to get a little bit of rain over here, not just drizzle, but drizzle and rain associated with nimbostratus clouds. Remember again, nimbo, rainy, stratus, those gray clouds that blanket the lower elevations. Nimbostratus in the Crescenta Valley. Later on that same day, from the prior picture of stratus clouds, we actually did get some rain as the air was forced to rise a little bit more, cool off a little bit more, and finally give up some rainfall. At that point, the stratus clouds become nimbostratus clouds. Cumuliform clouds, in fact, this is a cumulus cloud, flat bottom, white puffy sides and top, usually associated with fair weather, but these can grow into those cumulonimbus clouds we talked about, such as this. This is a beautiful cumulonimbus cloud here, that anvil top. You would not want to go inside here. You wouldn't want to fly in there because you've got updrafts and downdrafts, and if you're below there, violent rain, hail, thunder, etc., associated with clouds such as those. Another beautiful cumulonimbus cloud here. And finally one, here we go, right here, cumulonimbus. You should be able to identify that clearly now as a cumulonimbus cloud. This one over here has a cumulus cloud. Nimbostratus with the rain associated with it. Stratus, horizontally layered, but no rain. Cirrus clouds over here, high altitude, made out of ice, blown by the upper level winds. Wispy looking clouds. So some questions for you. So which clouds have flat bottoms, puffy white sides, without giving us any rainfall? You should be able to answer that at this point. Which clouds are composed of ice crystals and appear like horses' tails? What's the main difference between a stratus cloud and a nimbostratus cloud? Which clouds are associated with hail, thunder, lightning, heavy rainfall? I think you could probably answer each of those pretty quickly at this point. What kind of cloud is this? This is taken from the Glendale College campus, looking towards the north. And that cloud is probably over Palmdale, maybe some 30 miles away. You can tell how big a cloud like that must be. And it's got this beautiful anvil shape over here, sheared by the upper level winds. Inside here is probably some major updrafts and downdrafts providing heavy rainfall, lightning, and thunder. I think you know what kind of cloud that is by now. Okay, so when air is cooled adiabatically, that means the air is going to be rising up into the atmosphere. We haven't addressed yet how that uplift occurs. Why does air move up into the atmosphere? Now, we have discussed it in other terms in other chapters, but we haven't divided it up into the mechanisms for uplift that we're going to see right here. First and foremost, convective uplift. So convective uplift involves convection. And convective uplift just means that at the surface of the Earth, remember that's where we absorb most energy, where the Earth absorbs most of the solar energy, that's going to warm up the air molecules above the surface, and those air molecules are going to rise. As they rise, we see one mechanism for air moving upwards, cooling adiabatically and forming clouds. Now, the key here in this word is convection. If you remember, that involves both the vertical and the horizontal movement and mixing of air. And sometimes we see people split the upward movement as the upward force, the thermal action, the thermal elements driving this system, versus, remember here, air is going to split at high elevation, move down, and come back into that low pressure area where the air is rising. Well, some people say air moving across the surface towards a low pressure system is enough by itself to make air rise. And they call that, if the movement of this air, this horizontal movement, is enough to drive the upward movement of air where these air masses converge, or sorry, where this air converges, they would call that convergent uplift. I don't see a way of splitting these two. For instance, at the equator, the air is warm, the air rises, and that will give us cloud formation. That air will then, at about 50,000 feet, it will sink down and find its way back to the equator. So it goes up at the equator, down at 30 degrees north and 30 degrees south, back to the equator. So these would represent, in this diagram, the trade winds, converging at the equator to a low pressure area and rising up. So for me, it's a little bit hard to differentiate these two, and oftentimes I will refer to this as convergent convective uplift or convective convergent uplift. Some people like to split those up into two different processes. Either way is fine. So you can refer to this as convective uplift and this is convergent uplift, or both as convective convergent uplift. Again, for me, it's hard to split those up. Another way to get air to move up into the atmosphere is for the air to be forced over higher topography, maybe over a mountain, over a hill. And we call this topographic uplift or orographic uplift. Same thing, topographic or orographic uplift. And lastly, another way to get air to move is if cold air and warm air converge with each other. If the cold air is doing the moving, we'll learn in the next chapter, that's called a cold front. And if the warm air is doing most of the moving, we refer to that as a warm front. So we're going to discuss fronts in our next chapter. But in this diagram here, cold air is more dense, usually a little bit drier because cold air cannot hold as much moisture. But if it moves into warm air, it's going to force that warm air to go up and cool adiabatically. It will provide us with clouds and possibly with rainfall. But basically, this is a way to get warm air to move. The reason the clouds are over here, by the way, is that warm air can hold more moisture. And as that warm, moist air rises up, it will give up its moisture pretty readily. So just a look here at convective. Sometimes people call it thermal uplift. Convective uplift here. Convergent uplift. Again, for me, hard to separate those two out because we have convergence in the convective uplift. Orographic or topographic uplift, air is moving up. We have cooling. We have cloud formation. As it sinks down the other side, we get very dry air, drying and warming up very, very quickly. That's one of the reasons why we might have some moist environments on one side of a mountain. We call that the windward side. And we have very dry areas on the other side, maybe even deserts on what we call the rain shadow. So rain on this side, no rain on this side, we call that the rain shadow from orographic or topographic uplift. And then we have frontal uplift. We can see in this diagram here, we have the cold air moving in from right to left, pushing the warm air up, and that warm air will cool, give up its moisture, and probably give us some rainfall over here. This with the cold air or cooler air doing the moving, we would call that a cold front. If the warm air is doing most of that moving, we call it a warm front. In either case, we call those fronts, and the type of lifting, frontal lifting. So with all that, we also have to look at, it's a geography class, where do we get most precipitation on the planet? And putting all the things together, we can say, wow, if we got warm air that has a lot of moisture and it's forced to rise up, it's going to give us an awful lot of moisture. And that is indeed the case. If we look at right along the equator, the darker blue means more rainfall. So very close to the equator, lots of rainfall, lots of rainfall, lots of rainfall. So very clearly, the equatorial regions, we have warm conditions, we have moist conditions, we have rising air because of the ITCZ. That is the place on the planet that typically will get more moisture than anywhere else. Okay, as we get towards the end of this chapter now, I'm going to talk very briefly about clouds and fog. You've seen clouds, we've discussed clouds. We're about to discuss fog. So what's the difference between them? Well, first of all, clouds are aggregations of water droplets that are suspended in the air. Now we can see water droplets where we can't see water vapor. So the water droplets will reflect light. Water vapor will not. So we can see the reflection off the water droplets, but these are in the air above the ground and they formed. All clouds form from air rising and cooling adiabatically. So we wouldn't call it a cloud at ground level. That air has to rise before forming that cloud. So clouds are going to be in the sky. I know it sounds obvious, but that's part of the definition. Now, fog and clouds, if you took a sample of each, they're going to be exactly the same stuff. It's going to be aggregations of water droplets. But fog will form at ground level or very close to ground level. And fog does not form by rising and cooling adiabatically. Fog forms by air cooling at the ground surface. Overnight, cooling slowly. As the air cools, it gets closer and closer and closer to its dew point temperature. Relative humidity gets closer to 100%. And finally, when things are at 100%, but relative humidity is 100%, we would see the air where we didn't see the air before because we now can see the water droplets suspended in the air. So again, fog forms at the ground by cooling off naturally on a day-to-day cycle. And that cooling period will reach a minimum temperature around sunrise. So that's the best chance of getting a fog. Now we get fog when the air is cool enough. And our chances are better in the winter than the summer because we start off with cooler temperatures typically in the winter. Also in winter, nights are longer, days are shorter. Now if we have those conditions, a winter night, cold conditions with some source of moisture, and a lack of wind, so we get very calm conditions, because wind will just kind of mix everything up, mix the warmer air and the colder air in a local environment. If those get mixed up, we probably won't get a fog. But if things can stay still and slowly cool off, and we don't have any clouds holding in the thermal heat escaping the surface at nighttime, we can get really nice conditions for fog to form. So cold winter nights with calm conditions, clear skies so we can get the energy radiating away without being trapped by clouds. That's a good chance of us getting a fog. Now, when you have fog, it's very hard to see from one place to another because you're seeing the droplets of water in between. Now, something related to fog, but of course, where the air is not filled with suspended particles of water, but instead we see a situation where objects have cooled off to below the dew point temperature of the air. So again, probably a cold, calm, clear winter night, but hasn't gotten cold enough yet for fog to form. We can often see little drops of moisture on even colder objects, like a car. Your car cools off a lot more efficiently than does the air at nighttime. And if your car cools off to below the dew point temperature of the air in the early morning hours, any air touching the car would leave its moisture droplets on that car itself. I mean, think about that. You touch a car in the early morning hours, your hand feels cold. Air touching that car in the early morning hours, the air feels cold, and it might cool off to below its dew point temperature and drop little portions of liquid moisture onto that car. And those little droplets we refer to as dew, D-E-W, dew. Now, if that car is colder than 32 degrees Fahrenheit, instead of leaving droplets of moisture, of liquid moisture, it would leave a blanket of or sheet of thin ice that we refer to as frost. So dew, condensation of liquid droplets onto cold objects, whereas frost is deposition of ice crystals onto very cold objects. How cold? Colder than 32 degrees Fahrenheit. Here's some examples here. Clouds up in the air. Now, on a cloudy day, you can still see clearly at ground level for most intensive purposes. But you got a kind of a gray, dull sky here. Hey, any guesses as to what type of clouds those are in this particular environment or that particular day? There was no rain, maybe a little bit of drizzle. If you guessed correctly, those would be stratus clouds. If there was rain, these would have been nimbostratus clouds. Whereas fog in this diagram here, see it's hard to see across Tower Bridge here. This is Tower Bridge in London. That's not London Bridge. London Bridge is quite a boring bridge, but this one, Tower Bridge. It leads to the Tower of London on the north side of the river there. By the way, that river is called the Thames, T-H-A-M-E-S, the Thames River. It sounds like it should be spelled or pronounced Thames, but it's not. That's the Thames River in London. So here's the fog. Fine suspended particles forming at or near the surface of the earth, and we can tell we've got clear skies above here. So this is definitely fog. Dewdrops. The car in this example cooled off to below the dew point temperature of the air around it. So these are little drops of dew. Those are liquid. Whereas frost occurs when, in this case, the car was colder than 32 degrees Fahrenheit. So the air deposited a layer of ice on there. You need an ice scraper to get that off. To tell you the truth, if you have an extra credit card, one you're not using very much, that also works as an emergency ice scraper. Just be careful because they can shatter when they get very cold. So there are four basic types of fog. The first type is called radiation fog. Sometimes that's called valley fog. And this type of fog will occur because in cold, clear, calm nights, the cold air settles into low spots like valleys. So we might get the coldest air down in the bottom of a valley, and that might be just cold enough for fog to form within the valley. And if it's a clear night, all night long, we've seen energy and heat escaping into that clear sky, making the surface colder and colder and colder. So the coldest places are going to be in the valleys because the cold air will settle down into that valley. So that's called radiation fog, valley fog. In California, we call one variety of that Tule fog, T-U-L-I, so Tule fog. And that occurs as you drive from LA up to San Francisco or Sacramento on Highway 5 or Highway 99. You can get this Tule fog. And truly, that is a nasty fog because it will appear in a matter of minutes, and then you can't see even your hand in front of your face. So imagine the traffic in front of you. It creates a very dangerous situation. Another type of fog is referred to as advection fog. Now, remember that word advection? That means the horizontal movement of air. So advection fog would be the horizontal movement of fog. So we can have fog form in one place and move to another. So we can have fog form off the coast of California, like maybe off the coast of San Francisco, where we have a cold ocean current chilling off the air as it moves in towards San Francisco Bay. And since it's moving horizontally, we will call that a advection or an advection fog. Again, advection fog. Now, if it forms off the coast but stays off the coast, we couldn't yet call that an advection fog if it's not moving. We would call that instead an evaporation fog. So an evaporation fog is a type of fog that will form over a river, a lake, a bog, a swamp, an ocean. So it's forming where the air is saturated with moisture, and that air doesn't have to cool down quite as much as the air around it. Now, again, if it formed in this one place over the water and started to move, we'd have to call that an advection fog. But while it's still over the water, we call that, in this case, an evaporation fog. So evaporation fog forming over the water. If it's moving, or when it moves, so when it's formation place to another place, we refer to it as advection. And our last type of fog is called upslope fog. It's moving upslope. And chills off against the cold surfaces, tops of hills, mountains, and that fog sticking very close to the mountains will be referred to as an upslope fog. There's some photos of each of these in just a second. So there's an overview of your four main types: radiation fog, evaporation fog, advection fog, upslope fog. But the pictures are worth 1,000 words, so let's look at those real quick. Advection fog, forming in one place, moving horizontally to another place. I think you've got that idea down now. Upslope fog. This is air that will condense at its interface or as it interacts with the surface of a mountain or a hill. Radiation fog, like this Thule fog. This is shown in the Central Valley of California and how thick that fog can be in there. And basically, radiation fog forming in valleys, the air settling down, the cold air settling down in the early morning hours into the lowest spots. That happens to be where we put a lot of our highways too. And basically, this radiation fog could form very, very quickly. For those of you in Glendale, you might see the downtown Glendale, a little bit lower in elevation than the GCC campus. And there might be mornings when you wake up and it's foggy down by downtown Glendale, but you come up in elevation just a little bit and there's no fog on the Glendale College campus. And lastly, evaporation fog. So this is that fog that will form over, basically over water. So over a lake, over a river, over the ocean, over wetlands. And this is a very nice picture of evaporation fog. Gives you the idea of what's going on there. So those are the four major types of fog. I just have to find my cursor here again. There we go. Okay, so some questions for you. What's the main difference between dew and frost? Will you be able to tell me that? If I ask you that as a short answer essay question. Under which conditions would fog be most likely to form? So under what types of atmospheric conditions would fog be most likely to form? I'll give you a clue there. We're looking for long, cold, calm, clear winter nights. And what time of day would fog be most likely to form? And remember, when air temperatures at the surface are the coldest, that's when your chances of fog forming would be greatest. So really you got to answer, when is it coldest in any given day or in a typical day? What's the difference between evaporation fog and advection fog? What if I asked you that question? Which areas on Earth receive the highest annual precipitation, highest amounts of annual rainfall? And lastly, what's the main difference between how a cloud forms and how fog forms? So clouds and fog, they pretty much look the same, but how do they form differently? What is different about how each of those form? So a question for you to ponder. I wish you well on these. These will be good preparation for your upcoming exam. And of course, when we meet in class or when we meet online for our online class, we'll be certainly be able to answer some of these questions if you can't find the answers yourself. Okay, talk to you soon.